What if I told you that generating electricity was as easy as poking a rock?
Yep, it's that simple. I'm Joy Patterson, and today I will be explaining the piezoelectric effect. Back in 1880, two brothers, Jacques and Pierre Curie, first discovered this phenomenon. They realized that when they applied mechanical stress, basically a stretch, poke, or squeeze, to certain crystals, an electrical charge was emitted. To understand why this happens, we need to take a closer look. Originally, the charges of each molecule in the crystal are balanced with each other. But when force is applied to the crystal is deformed and the molecules actually move so that all the positively charged molecules go to one side and the negatively charged ones to the other. It is this separation that causes a current to appear. A year after the Curie brothers' discovery, another scientist named Gabriel Lippmann mathematically deduced the existence of a converse piezoelectric effect. The converse effect can be boiled down to this. When an electric field is applied to a piezo crystal, the crystal is mechanically deformed, which basically means it is stretched or flattened. Okay, it's pretty cool that we can generate electricity from hitting a crystal, and that we can make a crystal change shape by putting electricity through it. But what is this crystal we keep talking about?
A quick background in crystals. Every molecule in a crystal has a polarization, meaning one end is more positively charged and the other more negatively charged. This can be represented by an arrow that physicists call dipoles, not to be confused with dimples. Anyways, for a crystal to display the piezoelectric effect, all the dipoles must be pointing in the same direction. That said, there are two types of crystals out there, monocrystals and polycrystals. The first of these, monocrystals, has dipoles that are naturally aligned, which means they are naturally piezoelectric. The second type, polycrystals, have dipoles that are naturally randomly aligned, but when subjected to an electric field, the dipoles align perfectly. Once the electric field is removed, the dipoles shift so that they are not perfectly aligned, but enough so that they still produce the piezoelectric effect. This process is known as poling.
Okay, I'm done with the technicalities. It's how we can apply this principle that's really amazing. When you use a lighter and pull the trigger, it's actually hitting a piezo crystal, which lets out a spark and lights the gas. In sound birthday cards, electrical pulses are deforming a piezo crystal, which is letting out sound waves. Ultrasound and sonar both use piezo crystals to generate high-frequency sound waves.
Though relatively untapped, piezo crystals have great potential for generating energy, especially in the middle of our current-day energy crisis. In a few years, simple tasks like running could be generating electricity.
I hope you learned a thing or two about piezoelectricity and that I made this video crystal clear. Thank you for watching.